Hello, this is Suhan Kim, and I'm working with Professor Kevin Chen at MIT. And today I'll be presenting a firefly-inspired insect-scale flying robot that can generate light during the operation. So light production in natural fireflies perform various functions, such as evading predators, attracting prey, mates, or communications. And since we are developing insect-scale flying robots, such lighting up functionalities can benefit our robot in various ways as well. For instance, we can use light for visual communications, or we can also track pose of the robot using the light sources. However, since our robot is in very small scale and lightweight, there are several challenges of putting lights on our robot. First of all, since the robot has limitations on payload, we might want the lights to be lightweight as well, also the accompanying parts such as wires. Also, considering the efficiency, we might not want to consume substantial power to the light. And of course, in the meanwhile, we have to maintain the robotic performance with the lighting up functionality embedded. Some of you might heard of it already, but our robot uses so-called dielectric elastomer actuators, or DEAs. The DEA consists of the elastomer layer sandwiched by two electrode layers. So if we apply voltage across these electrode layers, electrostatic force causes the expansion of the elastomer layer in certain direction, which ultimately becomes the actuation. For DEAs, there is a unique way to achieve light, which is utilizing so-called electroluminescent particles, such as zinc sulfate. So these particles emit light when AC electric field is externally applied. So using this phenomena, the researchers have developed diverse soft matter devices by simply embedding particles into somewhere in their devices. So basically, these particles react to AC electric field. But however, in most cases, the operation of DEA requires DC input rather than AC. So what people had to do is either putting additional layer that is only dedicated to lighting up the particles, or applying additional input power to light up the particles. However, since our robot already uses AC electric field for flying, embedding those electroluminescent particles into our robot can get away with those redundancy, which means that we can generate light with very small weight increment as well as very small additional power. So it's pretty well suited. One challenge of embedding particles into our DEAs is that the particles are basically the foreign materials that damages the quality of the elastomer layer. And this ultimately reduces the voltage range that the actuator can survive. However, what we have come up with is that taking advantage of the fact that our DEA is in rolled up structure, we don't really have to embed particles within the intermediate, within the elastomer, within the electrode layers. But what we can do is that we can embed particles either on the very top layers or on the very bottom layers, which actually contribute a lot to the electrical breakdown of the actuator. So we fabricated and compared the case where the particles are embedded in one of intermediate layers versus the case where we embed particles on the very top layer. So what we clearly observed is that if we embed the particles on the top layer, we were able to achieve comparable voltage range with original DA, whereas if we embed particles inside the electrode layers, these particles will gradually damage the performance during the operation of the robot. Then we developed two types of electroluminescent DA fabrication, one good for fabricating single color DAs in upper stream, and the other one good for fabricating patterned color with different colors. So here's the picture of our robot prototype with different color ELDAs, and the one with patterned light in MIT letter with all alphabet in different colors. Thanks to our embedding strategy, we were able to maintain comparable performance to the original DA without electroluminescent particles in terms of mechanical and electrical properties. And especially for weight, we only added 3 milligrams, which corresponds to only 2.5% of total weight of our actuator. Next, we characterize the luminance or the brightness of our actuator with respect to the driving voltage and driving frequencies. When we increase the voltage up to 2 kilovolts and the frequency up to 450 hertz, the brightness grew along the voltage and along the frequency in all the colors. So in the operating condition of our robot, which is marked in yellow in both graphs, the brightness of all particles were in the range that we can detect with our bare eyes. We successfully achieved 5-second hovering flight with the robot driven by 4 lighting up DEAs. And here is the flight recording of our robot using both high-speed cameras and 3 off-the-shelf smartphone cameras. Actually, what we actually aimed during this experiment is to testify if we will be able to switch our previous infrared motion capture system to much simpler vision-based tracking. The reason is that our previous infrared motion capture system consists of 6 heavyweight cameras. So if we can replace those into smaller scale cameras, they can be pretty crucial contribution to our research. For that, what we really have to testify is that we have to achieve high quality position and orientation tracking capability. Thus, using the recorded video from 3 smartphone cameras, we post-processed the video and tracked the position of 4 DEAs, which ultimately gives us 6 degrees of freedom pose of the robot in 3D space. And we compare the result with our previous infrared motion capture system. So result was pretty impressive that during the 5-second hovering flights, both tracking methods, so vision-based tracking method versus infrared motion capture system or Vicon system, resulted in the position error of only 2.5 millimeters and the rotation error of 2.6 degrees. This result suggests the potential of our vision-based approach to be used for feedback control system in the future. And then it can make the hardware setup much smaller, simpler, and cheaper. So in summary, we introduced a electroluminescent DEAs, and we were able to demonstrate position and additive trackability using small scale cameras. And for future works, we might want to achieve turning on and off capability, and then also build the control system only using vision-based tracking system. And thank you.
Thank you very much.